So first off, let us understand the textbook definition of RAGs. RAGs is a method where we combine LLMs with a retrieval system. This retrieval system can search through vast sources of external information like documents, databases, or knowledge bases whenever the LLM needs additional information to give you better answers. At the same time, it also makes sure the LLM is not overloaded with bigger prompts. Let's say you're working at a company with hundreds of internal documents like policy guidelines, technical specs, customer support documents, etc. Now, if you have a question that could be answered by one of these documents, it would be unrealistic to dump all 100 files into the LLM and ask that question. It is unrealistic because LLMs have a context window, meaning a limited number of information it can process at a given time. But with LLM plus RAGs, this process can be streamlined. So the next time when you have a question, you can just ask the RAG system in simple English and it retrieves the most relevant information from these documents and uses it to give you an accurate answer. Alright, so here is a simple visualization about the context window of these models. Okay, so if you do not know what context window is, you can think of it as a context window is like the amount of information that an LLM can process at a given time. So let's look at the first model. Okay, we've got GPT 4.1. You can see that it processes up to 1 million tokens. A token is basically one token. You can think of it as one English word. Okay, so it processes up to 1 million tokens. Anything above that, it is going to forget it. Okay, so we've got GPT 5. It processes 400,000 tokens. Claude 4, Claude models like Sonnet models, they seem to process 200,000 tokens. Now you might think, okay, that is a huge context window. Why do we have to use RAGs? Why can't we just dump all the PDFs, all the company documents to the LLM and ask a question? But if you actually look at the amount of documents that enterprises tend to have, you can see that enterprise data center, they have 1 petabyte worth of documents. That is an absurd amount, right? This is 1.3 quintillion tokens. This is like 10 to the power of 15 zeros, right? And even if you look at a large or a mid-sized company, they have 100 GBs or 1 TB worth of documents, and we cannot possibly dump all of that into the context window. Okay, it is just not going to be enough. So that is exactly why we need the RAG system. So before we look into what the RAG system is, let's try to understand what are tokens in depth. In the context of language models, a token is a unit of text that the LLM model processes. Tokens can be as short as 1 character long or as long as 1 word, depending on the language and structure of the text. For example, the word hello is 1 token, while the phrase I am is typically broken down into 2 tokens, I and M. Understanding tokens are crucial because LLMs have a limit on how many tokens they can handle at once, referred to as a context window. Okay, that is exactly what we saw earlier. This means if we have a PDF that is 10 million tokens long, we cannot possibly feed it to a model in one go. So this is why we need a smarter system called retrieval augmented generation. On a very high level, I want you to think of retrieval augmented generation, the entire system, into 2 different parts. The first part is going to be the ingestion pipeline, and the second part is going to be the retrieval pipeline. Okay, so we are going to break it down. We are going to, divide and conquer. Okay, let's first try to understand this first part, which is the ingestion pipeline. So at the start, we have the source documents right here. You can think of it as a lot of PDFs or CSV files or PPTs of a company. Okay, so this is the entire knowledge base. And this particular source documents has cumulatively 10 million tokens. This is just an arbitrary random number at this point, but you can just consider it to be a lot of documents. So in order to build out this RAG system, the next step that we have to do is something called chunking. Chunking is the process of breaking down bigger documents into smaller chunks. That is exactly why we call it chunking. So we can actually set the total number of tokens that each chunk needs to have as 1000 or 2000 tokens or 3000 tokens. But in our example, we are going to set it to 1000 tokens. Okay, so to give you a very simple example of how the chunks would look like, let's actually take an example of a PDF. So what I have right here is basically I've just downloaded the chain of thought prompting PDF. Okay, so let's go to page number 2. And if I wanted to chunk this entire document and set the upper limit to be 1000 tokens, then basically it's going to be like this. So the first chunk is going to be, somewhere till here. Maybe this is the first 1000 tokens. And then this is going to be the next chunk. So from here to here, this is going to be the next chunk. And then from here to here, this could be the third chunk. And this could be the fourth chunk. And this could be the fifth chunk. So coming back to our example, we know that our source documents cumulatively has 10 million tokens. Since we have set the upper limit of each chunk to be 1000 tokens, dividing 10 million by 1000, we are now going to have 10,000 chunks. I hope this particular part makes sense. Let's move on in the pipeline. The next step that we have to do is we have to pass these chunks through something called an embedding model. An embedding model is not the same as an LLM model. An embedding model specializes in a completely different thing. What it does is it converts English passages or words or sentences into its associated vector representation or a mathematical representation, you can think about it. Okay, so first chunk, let's say this is first chunk, it is going to convert that into its mathematical representation. Okay, the second chunk is going to be converted into its own mathematical representation. The same thing for the third chunk. Okay, so what exactly is this mathematical representation? So this is a pretty crucial concept that we will have to learn as full stack AI engineers. So let us actually dive deep into what are embedding models, what are these vector embeddings, why do we even do this? So what are embeddings? A vector embedding is a mathematical representation of words, sentences, or even images. For example, the word cat can have a vector embedding that can look something like this. So this is the computer's way of making sense of the word cat. Basically, each of these numbers can represent a certain aspect of the word cat, like small, furry, it could be a pet, right? So all this information is captured in this mathematical representation. Let's look at a few more examples. So right here you can see we have the vector embeddings of 4 different animals: cat, kitten, elephant, and dog. Okay, so these are arbitrary numbers, but just for the sake of learning, let's say these are the vector embeddings of these 4 animals. Each number in the vector embedding is called a dimension. So in the vector embedding of this cat, 34 is the first dimension, 8 is the second dimension, 7.5 is the third dimension. Words with similar semantic meaning tend to have dimensions that are closer to each other. So what this means is that, let's take a look at cat and kitten. You can actually imagine that they are both similar to each other, right? A kitten is basically a younger version of cat, right? So that is why if you look at the first dimension, maybe let's just assume that the first dimension talks about size. The second dimension talks about pet, this particular word, could this denote a pet or not? Okay, something like that. So right now you can see, since the first dimension is going to be talking about size, they are both closer to each other, right? 34 and 33, it could be the other way around as well, but you can see they are closer to each other. But if you look at an elephant that is completely different from both of these animals, this particular first dimension is very far away, right? Is very far away from 34 and 33. Okay, I hope that makes sense. Now I hope this is starting to click for you. Maybe the second dimension is going to be, how domesticated is the animal. So you can see 8 and 8. So cat and kitten are both domesticated. Whereas an elephant, it could be domesticated as well, but it's a little difficult, right? So that is why it is 62, which is far away from cat or kitten. So that is why we say words with similar semantic meaning tend to have dimensions that are closer to each other. So in other words, when a word's vector embedding is mapped in a multi-dimensional space, the spot where cat exists will be closer to where the word kitten exists. So what does this mean? So this vector embedding, let's look at it. So this could be the x-axis, this could be the y-axis, and this could be the z-axis, right? So you can actually imagine this 3-dimensional space where cat lives. So because cat and kitten are closely related to each other, the space where kitten lives is going to be very closer to the space where the spot where cat exists. That is the idea. And elephant is going to be a little more farther away. If you look at dog, it also has 8 right here because, okay, that is also a pet. Okay, so cat and dog are going to be a little closer to each other, not as close as cat and kitten. It is going to be a little farther away, but dog and elephant are going to be very much farther away because they are very different animals. Okay, I hope that makes sense. So here is a very basic diagram. You can actually use your imagination and visualize it. But right now you can see that, in this three-dimensional space, okay, I've basically mapped it in a two-dimensional space. But imagine this to be a three-dimensional space. You can see mango and apple live together because they are similar fruits, right? We have milk, tea, and coffee. They're all closer to each other. You can see tea and coffee are much more closer than milk because tea and coffee are a lot more similar to each other and milk is a little farther away. And here you can see cat and kitten are somewhat closer to each other. And dog, despite it being in the vicinity of cat and kitten, it's still a little farther away. And they're all very farther away from mango or apple because they are not fruits, right? I hope this makes sense. Let us move on. Even though we see 3 dimensions in each vector embedding, in reality, popular embedding models like OpenAI's text embedding 3 large transform text or paragraphs to up to 3072 dimensions in each vector embedding. So we can't even visualize it, right? I mean, we can easily sort of visualize a 3-dimensional space because our minds, we exist in a 3-dimensional world, right? But using mathematics, we can actually add a lot more different dimensions. So right here we have X and Y and Z, but if we actually use cat and then we use this particular model right here and ask it to convert it into a vector embedding, this particular vector embedding, okay, so this list of numbers, dimensions, this is called a vector embedding. And this vector embedding is going to have 3072 dimensions. That is a crazy amount of, information that is going to be packed. Note that if we embed a small word like cat or a large paragraph, we always get one vector embedding output that has 3072 dimensions. The advantage of using higher dimensional embedding models is it captures more semantic information about a text passage. The downside is that it is slightly more expensive to embed as well as store. Let's look at some of the popular embedding models out there. There are many embedding models out there, but let us focus on the most popular ones you will encounter. The first one is obvious, OpenAI's, which is the most popular choice. And OpenAI provides 2 different models which are very popular. We've got the text embedding 3 small model, and the default dimensions that it provides is 1536 dimensions. It is great for most use cases, but we can actually reduce it to 512 dimensions, 1024 dimensions, or anything below 1536. Let's look at the next model. We also have text embedding 3 large, and this by default provides 3072 dimensions. This provides the best performance, but it also costs more. It can reduce to 256 dimensions, 512 dimensions, 1024, 1536, or any size below 3072. So for this model, this is going to be the default dimension and it can choose any of these values below it. And for the large model, this is going to be the default and we can also choose any of these different dimensional values below it. So both these models lets you reduce dimensions to save storage costs without losing much quality. And some of the other notable players include Cohere. We've also got Voyage.ai, we've got Mistral. Okay, so if you can just check it out. You can go to, let's say, Voyage AI embedding models, and you can actually click on the first link, and now you can see we've got Voyage 3 large, Voyage 3.5, and this is the amount of information. This is the amount of tokens that we can pack into one chunk and then ask it to embed, right? So the amount of dimensions that it provides is 1024. So earlier we saw the OpenAI large embedding model provides dimensions up to 3072, right? So this is the largest. So for Voyage, it's going to be 1024. All right, so let's move on. So what is a vector database? So we know what vector embeddings are. Vector databases are basically built to store all of the vector embeddings, and that is what is considered as a vector database. So to store all the vectors, we can use a specialized vector database like Pinecone, VV8, ChromaDB, FAISS. So this is a vector DB that is built by Meta. Okay, so you can see this is built by Meta, Facebook AI Similarity Search. We can also use regular SQL databases like Postgres. Okay, so it provides structured data storage and retrieval. So let us now come back to our RAG system. Okay, so right now you can see all the chunks have been converted into their associated vector embedding. And now we have 2000 different vector embeddings right here. And now we are storing all these vector embeddings in the vector database. So now you might have a question, why do we even have to convert English passages into a mathematical representation? Why do we even have to do it? So we will see why that happens in the second part, which is the retrieval pipeline. And now let us look at the first step. The first step is, the user, it could be you or me, we are asking a question to the RAG system. The question could be, tell me all the sales that happened in last year, first quarter, or something like that. So here is what's going to happen. This query is going to, again, similar to what we did here, this English query is going to be converted, passed through the embedding model, and it is going to be converted to its vector representation. Okay, the same thing that we did here. So right now, what do we have? We have all of the source documents that are present in the vector mathematical representation format. And we also have this user query that is also in the mathematical representation format, which is a vector embedding. So now that we have done this, so what this retriever component, okay, this is going to be the next step. What this retriever component is going to do is it's going to take this particular data and then it's going to go through all these different vector embeddings and see which one is closer in semantic meaning to the user's query. Let's say the first chunk is talking about something completely different from sales. It could be talking about product. Okay, we don't want this. But let's say the second chunk talks about something related to sales. So in this case, comparing this information and this information, there is going to be some similarity. How exactly the similarity is going to be calculated, that we will see later on in this series, but there is going to be some similarity. So if there is some similarity, this particular chunk, along with its original passage, they are going to be shortlisted. Okay, so we can actually tell the retriever, get me the top 5 most relevant chunks from the vector DB based on the user query. So that is exactly what the retriever has done. So because the user's question was about sales, these 3 or 5 or 10 chunks, the top 10 chunks, they are going to have passages which talks about sales. Okay, so now what do we have so far? We have the user's question, and now we have potentially 10 different passages or chunks, okay, that talks about sales about one particular year. Okay, so now what we are going to do is we are going to send all this information to the LLM. So that is what we're telling the LLM. We are basically telling the LLM, hey, this is the user's question. These are all the different chunks or English passages that could potentially have answers to the user's question, and then try to answer it. And then the LLM is going to give an answer. So here we are only going to deal with the original chunks. Okay, these chunks have English passages, right? We are not going to deal with vector embeddings after this particular point. The vector embedding is just to do the similarity matching, which we will look at pretty soon about the algorithm, how it matches things. But it's only for the matching that we use the vector embedding for. We don't use it after this particular point. After this particular point, we only deal with English. I hope that makes sense. This is how the RAG system works. So to summarize it, this is how a RAG system works. We could have 10,000, 50,000, 100,000 different documents. We are going to convert all of that into its vector representation. So now that we have the vector representation ready, the user query is also going to be converted into its own vector representation. And then we are going to do some matching. Okay, that matching we will look at later on. But we are going to match, we are going to retrieve the top 5 or 10 different chunks that matches with this particular vector embedding. We are going to retrieve that. We are going to retrieve the original passages, and then we are going to send to the LLM along with the user's question. Now I want to talk about one more thing that beginners usually make mistakes when they're building RAG systems, and that is consistency. You must use the same embedding model for both your documents and your user queries. Think of embeddings like different languages. If you embed your documents using the text embedding 3 small model, but embed user queries using a different model, they literally cannot understand each other. Even within the same model, you must use the exact same dimensions everywhere. For example, if you embed your documents using text embedding 3 large with 1536 dimensions, you must also embed user queries with the same dimension and same model. Pick one embedding model at the start and stick with it throughout your entire RAG pipeline. If you want to switch later, you will have to re-embed all the documents. And that is it for this video. In the next video, we will start implementing the first part of the RAG system, which is the ingestion pipeline. So I'll see you in the next video.